赶快第二节课横过来，我去，真的是。
会看那个 mark 吗？那个 numerical analysis。
哦，可
收上去了，收上去了。
没收。
哦，看一眼。
等一下，我回来的。
谢谢你。
不是平行。对，应该不是。所以我就在想，就是说我非常能够理解，假设我不看这一段的话，我就把2x 就1和负1直接作为福瑞因，就这个单独出现，我觉得很合理。但是他说他想把这一步用这个思想导到这一步，我觉得中间就会出现很多问题。
那你从这一步到下一步是什么样的？
这一步到
这两步是一步，这两步。
哦，对，就是我。OK， 就是我感觉就是说，比如说我们认为 x 的绝对值的更 general 的 derivative 就等于1和负1去到0点，这件事情非常符合 intuition， 但是如果真要严格说的话，我们还是得把这个结果积回去看。
Okay, so probably it's better for us to start with the second part. Okay, and so with so many discussions, okay, about delta function, I think we already have I mean, not completely rigorous, but at least more rigorous knowledge of delta functions than before. Therefore, we will be able to try to reapply the knowledge for the delta function to view everything that we are not exactly technically, but actually some of the materials, okay, in chapter 3, okay, in chapter 6. So if you still remember, can anyone tell me if I am talking about a solution? If I'm talking about, let's say, if I'm talking about the let's say the diffusion equation ut equals to k uxx. Actually, ut minus k uxx equals to fxt. Okay, for x to be defined on the whole real line, and to t to be defined as large as 0. Can anyone tell me how to solve that equation, which is the inhomogeneous version of the diffusion equation? And fxt means that there are, besides the initial condition, there are actually heat flows coming into the system everywhere, every time, from place to place, from time to time. Okay, for arbitrary x and t. So does anyone still remember how to solve that equation?
Fourier series.
Fourier series? You are really sure about that? Fourier series works for what type of problem? Please. For boundary value problems that are located within certain interval, right here, what is the definition? What is the domain for x? It's the whole real line. Right, it's the whole real line. So if you have forgotten this, then probably it's a good time for you to come back to view page. Let me see, page 67. Okay, page 67. Then you're going to find and the equation 2 on page 67 is your answer. Okay, so I'm going to write it down first. So that's actually uxt equals to the integration from negative infinity to positive infinity as x minus y, phi y. Here, phi is the initial condition, phi, and then plus the integration from 0 to t, the integration from negative infinity to positive infinity as x minus y, okay, and then t minus s, and then f y s dy ds. So is it good? So good. This was the formula. This was the solution formula for the inhomogeneous diffusion equation. Okay, that we deduced at that time. Do you still remember how we deduced this formula? Why the source function is participating in the solution for twice instead of once? The first part is actually easy to understand, right? Because that only takes account of the initial condition, which means that if my f is completely 0, then this solution would simply be the general solution. Sorry, the general solution to the homogeneous equation. Right? Then why does S participate in the solution again, and working with the inhomogeneous term F, or the source term F? Anyone remember what we said at that time? We were saying something like, okay, if we chop the system into pieces on time, then the source means that for every time step, okay, for every time step, there is an extra amount, okay, of masses, okay, or the extra amount of heat that is injected into the system. And from that time on, okay, this new coming part is going to diffuse as usual. It's going to diffuse as if that were the initial condition. And since the whole system is linear, then what we can do is just simply integrate, just simply do a linear combination for every for the solution starting from every single time piece. Okay? And here it comes out the integration from 0 to t. That actually stands for the linear combination. Okay, that stands for the linear combination for the injection at all time. Right? This is our. If you are unfamiliar with this, go back and check the lecture note. Okay, we did I think I did a pretty good illustration of this on that class. But today, the topic today is delta function. Okay, so instead of talking about this, we will be saying that. Okay, we'll be saying that. Let's say that R. Okay, let's say Rxt. Let's say Rxt is exactly Sx minus x0 and t minus t0. Okay, S minus x0 and t minus t0. Can you please tell me what is Rt minus krxs? Again, S is the source function. S is the source function such that S x0 is exactly the delta function. Can anyone tell me what does it mean by Rt minus krxs? If my Rxt stands for Sx minus x0 and t minus t0.
Just differentiating source function.
Sorry?
Just do the differentiation to the source function.
Okay. Go ahead. What do you get? What would you get? Okay. So this is basically, you see, this is basically S x minus x0, t minus t0, okay, and then t minus k s xs, x minus x0, and t minus t0. Is that right? Okay. If we were not having these x0 and t0, x0 and t0, what we would have? If the x0 and t0 are both 0, then what would we have?
0.
Is that 0
F
everywhere?
fx.
Is that 0 everywhere? What about when t equals to t0? What about when t equals to t0? So instead of 0, so which means that okay, which means that if when we are here, when the x and t are not exactly 0 and x0 and t0, then of course we'll be obtaining 0. okay, on the right hand side. However, don't forget s has a singularity. Don't forget s has a singularity. So when we are doing the differentiation, okay, and finally we will be obtaining, okay, something that's called delta, okay, x minus x0 multiplied by delta t minus t0. Okay, this can be verified by some of your homework. Okay, this can be verified by some of your homework. Well, again, which is this? Which is this? Well, can you please tell me what is the relation between f xt and delta x minus x0 and delta t minus t0 multiplied by t minus t0? First of all, if we are only having one dimension over here, if we're only having one dimension, which is x, okay, let's ignore the t part. Okay, let's ignore the t part. So no t over here. If we are only looking into fx and the delta x minus x0, what's their relation? What's their relation? What is their relation? We would have is that fx, okay, and then convolution with delta x is going to be what? Is going to be what? I mean, if there's no t, okay, if there's no t, what is it? It's going to be fx itself, right? It's going to be fx itself. Now, having the t, fxt, f is now a 2D function. Okay, f is now a 2D function. And now, convolute it with delta x minus x0 and multiply by delta t minus t0. Then what should this guy be?
I've evaluated.
It's going to be fxt as well, right? It's going to be fxt as well. So is it good? This part is okay? This step is okay? Okay. Why is that? Because this. Okay. So let me illustrate a little bit why this is true, right? Okay. So again, if in this case, okay, everyone can accept this, right? Everyone can accept this. So if in this case, what is the? Let's say we're talking about a function on the x and t plane. Okay. Now consider we're having a function on x and t plane. And how do we represent delta x? Only delta x, no delta t, okay? How do we represent delta x on this 2D plane? How do we represent delta x on this 2D plane? Which means that when x is smaller than 0, this is going to be 0. When x is larger than 0, x is not, delta x is going to be 0. But when x equals to 0, what will happen? When x equals to 0, this is going to be infinity, right? This is going to be infinity. Which means that delta x, okay, which means that the delta x, when represented on the 2D plane, okay, the delta x will have infinity on the whole t line. That part is okay? Okay. Which means that in this case, delta x itself is not, delta x only itself, okay, is not the delta function for the 2D function domain. If we want a delta function for the 2D function domain, okay, we need to multiply the delta t as well. Because, you see, considering another function, delta t is what? Delta t is only infinity at which place? At t equals to 0, when t equals to 0. Right? Okay, now, what's the product between the red and the blue?
Only infinity.
Okay, it's always 0 away from the origin. But it's going to be infinity at the origin. And the integration will still be 1. Right? The integration will still be 1. So far so good? Yes, go ahead.
But here, if, for example, we take x equals to x0.
Sorry?
For example, we take x equals to x0.
And?
Then the first delta should be infinity. But if t is not t0, It's
So this is actually, what does it mean by, okay, so this is actually something like, how do I put it? How do I put it?
Do we have something?
So an analogy for this can be considered in probability theory. Okay, try to use the probability theory. Okay, so the probability theory is in the probability theory, delta x means what? Delta x means that x is something. Okay, x is something that can only be located at 0. Okay? Delta t means that t is something that can only be found at 0. And then what does it mean by the product of two distributions? The product of two distributions means their joint distribution, and when these two random variables are completely independent. Right? And in this case, we obtain something that, because these two things, okay, the x and t, they are independent of each other, but they can only take value 0. Right? Therefore, their joint distribution is going to be 0 and 0. They will only have probability mass as 0 and 0. So what's good? And that probability is still 1. That probability is still 1. Okay, I understand that because we're talking about we are delving into the regime of infinity. It's everywhere. Okay, so it's a little bit hard to digest. Okay, what do you mean by this infinity? What do you mean by that infinity? Right. Okay. So accepting this, then using exactly the same idea, that we have. You see, we were looking for the solution to ut minus ut minus k uxx, which equals to fxt, right? We're looking for something like this. And therefore, you see, fxt can be written into the convolution of fxt and the convolution of delta x minus x0. Sorry, this is actually my bad. This is wrong. This is actually delta x multiplied by delta t. My bad. Okay. So fxt can be written into the convolution between fxt and delta x multiplied by delta t.
Professor, what do you mean by fx convolute with delta x?
Multiplied by delta t. So this is a 2D convolution.
No, I mean before, 2 lines before. The fx convolute delta x, you write 2x there. What do you mean?
You mean here?
Yeah. No, above. Yeah.
This one?
Yeah.
Fx. I'm talking about if we assume that f is only a 1D function.
Oh.
Okay. I'm assuming that if f is only a 1D function, okay, that is true.
Oh, okay.
Right. Okay. But the same thing is true because you see, 1D function can be regarded as what? 1D function can be expanded as to a 2D function for free, as long as we are keeping this 1D function to be a constant on the second dimension. Right. So the same idea for the 1D function also works for the 2D function. Okay. This is the only thing that I'd like to point out. Okay. And this is the right hand side. Right. This is the right hand side. But you see, if we can already solve, have the solution RT minus KRXS, which equals to delta x multiplied by delta t. Right? If we could already solve RT minus KRXS, which equals to delta x multiplied by delta t, then what would we have? Then the uxt will just simply be the rxt, okay, sorry, let me respect the old order, will exactly be f x t and then convolute it with r x. Okay, which here, again, convolution. So it's a good, this is of course you need a 2D convolution. This is the 1D. Okay, this is a 2D convolution instead of 1D. Okay, so this is the one idea about that. And let me give you another example. So this is the this is 12.2 and example number 1. Example number 1. Well, actually, doesn't depend. Okay, and then example number 2. Okay, again, when we were having, let's say u tt equals to c squared uxx. Let's say we're having that ux0 equals to 0. Okay, the initial when we're talking about wave equation, the initial condition is 0 on the place on the location, and the utx0 is psi 0 is psi x. Can anyone tell me what is the solution for u xt? What is the solution for u xt? What is the solution for u xt? Okay, you probably have a better idea about this. If this is not were 0, this were phi. Okay. If ux0 is phi, what's the solution? What is the solution? You have a better idea now, right? Which should be phi x
minus
minus ct, and then plus phi x minus ct, and then
plus
plus ct, and then
integration of
plus 1 over 2c integration of from negative from x minus ct to x plus ct, and then phi
of
dy.
y dy.
Right now, I'm just saying that this is 0, 0, 0, so we're not having the phi part.
Ah.
Okay. We're not having the phi part, we're only having the psi part. That is okay? So far so good? Okay. So, what I would like to ask you for is that, can you please first solve this equation, which is that STT, okay, let's solve another equation, SXT, satisfying that STT equals to C squared SXX, okay, and where Sx0 is also 0, but Stx0 is delta x. Stx0 is delta x. Can you solve this equation?
If what one?
It's actually the same. It's actually the same, right? So Sxt, I will be just simply using the equation, the solution that we have derived above, okay, because it is also satisfying that the initial condition that Sxt is 0, Sx0 is 0. So Sxt should be equals to 1 over 2c, and then doing what? Doing what?
X plus x minus ct to
Okay.
x
X minus ct, and then x plus ct, and then doing what?
delta y
x, delta y.
delta y dy.
Delta y dy. What is the result of this? What is the result of this?
It depends on.
It depends.
This, the integration of this, okay, is either 0 or 1. Depends on what?
Depends on the
Depends on if x minus ct
zero.
covers 0 or not. Right, depends on if x minus ct covers, from x minus ct to x plus ct, if that covers 0 or not. So is it good? So this should be what? So which means that my s minus sxt, my sxt only has 2 choices. It should either be 0 or 1 over 2c, right? So it's either 0 or 1 over 2c. When it is 0? When is my sxt 0?
When x is greater than.
That only happens when x minus ct be larger than 0 or x plus ct is smaller than 0. Right? So which means that only happens when x minus ct is smaller than 0 or x plus ct is larger than 0. So alternatively, when sxt is 1 over 2c, that should be x. That should be these two things. That should be these two things to be true. Okay, at the same time, which means that 0 is smaller than x minus ct. Actually, this should be yes. Okay.
Smaller than or equal.
And x plus ct.
Huh?
So good? So good? Okay. So what does that mean? That means that, here, this actually means that x, the absolute value of x is smaller than ct. Here it means that the absolute value of x is larger than ct. The absolute value of x is smaller than ct. The absolute value of x is larger than ct. So what does my st looks like? What does my sxt looks like? Initially, it's a delta function. Okay, initially it's a delta function, but sorry, my bad. Okay, sorry. Actually, initially it's 0. Initially it's 0.
看到了。
Sorry, my bad. Initially it's 0. But what happens from that? What happens from that? When my t is very, very small, what happens from that? It's going to be something like, okay, when t is very, very small, then a small beam, okay, which the height is 1 over 2c. Okay. So is it good? Okay. But you see, when t is very, very small, that means that the x over here, okay, the interval over here is also small, right? But when t is becoming larger and larger and larger and larger, that means that the place where the sxt is not 0 will become larger and larger and larger. So when t evolves, this will become something like this, and become something like this, and then become something like this. Okay? The speed that this interval expand will actually go what? It will go linearly. Okay, it will grow linearly. Okay, now again, you see, now again, don't forget, here, in this case, the initial condition was delta x. In this case, the initial condition was phi x. What's the relation between phi x and delta x? Again, my psi x equals to what? My psi x equals to psi convolute with delta x, right? My psi x equals to delta psi convoluted with delta. Okay, so that means that okay, the solution of this solution u, okay, if we were deriving from S, this solution u, okay, this solution u xt should exactly be sxt and then convoluted, okay, and then convoluted with phi y, sorry, with phi x. Okay, which is exactly now this we're doing a 1D convolution over here, which is the negative infinity to positive infinity s x minus y t, okay, and then phi y dy. What is that? Well, what is that? You have just learned what is we have just derived what is sxt, right? We have just derived what is sxt. SXT is something like this. Okay? SXT will either be 0 or be what? Or be 1 over 2c. So this is actually what? this is actually 1 over 2c, but the integrand should be go from where to where? The integrand should be go from where to where? The integrand should be go from where to where? Okay. The integrand should go from, okay, x minus ct to x plus ct phi y. Sound good? And this is exactly what we have deduced about using. So you see, this is what we, this is the old solution that we obtained, okay, at the beginning of chapter 2. This is the solution that we obtained, okay, using the idea of delta functions. Again, the idea over here is that I, first of all, for the initial condition, I chop the initial condition into many single pieces. Every single pieces can be represented by a Lego. At the level, this so-called Lego is my delta function. Okay? And then I solve for every single piece. I obtain an SXT. Okay? And then finally, for the solution to every single piece, SXT, I finally use a way to put it up. Okay? Come back to obtain the original solution because again, this is the linear system. This is the linear system.
Professor?
Yes.
But here we derive the source function.
You're right. You're right. You're right about that. This is actually more like a circular argument over here. I agree with that. Yes. Okay. And okay, so this is for diffusion equation and wave equation, and we probably don't have time to talk about the Green's function again, but one thing that we should again memorize, you should be already very familiar with is that the Laplace of 1 over 4 pi r is exactly delta x. Okay, is exactly delta x, and due to the idea of delta, due to the use of delta over here, then we are able to construct. Okay, we are able to construct. Oh, so well, actually, before we sorry about that. Before we move back to the Laplace equation, you see here I'm having an s over here, right? I'm having an s over here, and this s actually works for what? It actually works for arbitrary initial condition, and that can be done by a convolution, right? And compare this s and this s. You find a common. If you find anything in common, this s is what is the source function for the diffusion equation. As long as it's solved, we can apply that work straightforward in a straightforward fashion to any initial condition, right? And here again, this is another SXT, but this is for the wave equation. But again, it works for any arbitrary initial condition as long as we are we're not talking about initial condition for UX. We're talking about initial condition for UT. Okay. Once it is solved, okay, it works for arbitrary initial condition. Okay. So this can also be said, okay, as the source function for wave equation for speed, okay, for speed, for speed, okay, in the wave equation, okay, in the wave equation. Okay, so that's good. And now coming back to the Green's function. Again, the things that we should that everyone should already know is that the Laplace of -1 over 4 pi r. Okay, this is the delta function, but of course here my r is actually the square root of x squared plus y squared plus z squared. Is that this is at least okay 3D. This is actually at least a 3D in a 3D space. Okay, and in this case, we actually used this function, okay, to solve delta. We actually used this function to solve delta u equals to f. Okay, we actually use this function to solve delta u equals to f, which is a Laplace equation. But don't forget that this was actually this can be Laplace u equals to f, and then with actually, if we can come back to page 7 point. Yes, actually, if you can come back to page 190, okay, and then it will tell you that, okay, for the Laplace equation, the theorem 2 of on page 190, okay, page 190, okay, the Laplace equation, Laplace u equals to f, okay, for x in domain D, and u equals to h for x on the boundary of D, right? And now we are having ux equals to the integration, okay, the integration on the domain on the boundary of D, hx, sorry, let me say hy, and then partial g x. Of course, these things are y, okay, and then partial n, and then plus d, and then f x, and then well, actually f y, and then g x y dx. Sorry, dy. Right. Right. This is the g is the Green's function. G is the Green's function. Again, I don't have to get into detail about the specific definition for the Green's function, but by comparing this, okay, this again is the solution for the Laplace equation. Sorry, for the Laplace and Poisson's equation, right? But if we again compare this to, let's say, the diffusion equation, okay, to the diffusion equation, which is for the diffusion equation, actually the solution, the inhomogeneous diffusion equation, which we already talked about over here, okay? So let me just simply okay, and then duplicate. Okay. So the first thing, the first equation over here is the solution, is the generic solution, okay, to the Laplace equation. The inhomogeneous version is actually the Poisson's equation, and also with the help of the information on the boundary. The second one is what? The second one is also the solution to a homogeneous, but in this case, the diffusion equation. And we're not having the boundary condition, but actually we're having an initial condition, which is let me use this, okay, which is ux0 equals to phi x. Okay? Can you see the relation between these two formula? Can you see the relation between these two formula? First of all, what are the structures of these two formula? The first one is, okay, one thing adding another thing, the sum of two terms, okay? The first thing is that, okay, at first I do integration on the boundary, then I'm doing integration in the whole domain. The second is also one thing and add another thing. The first thing is doing integration, okay, not on the boundary, but on what? Okay. Only x-axis, right? The other thing is doing an integration in the whole domain. Okay. Now let's look into the specific. Now let's look into the specific structure of these two equations, formulas. Okay. So let's say this is my term 1. This is my term 2. This is my term 1 prime. This is my term 2 prime. 2 prime. Okay. I am actually deliberately asking you to compare the term 1 prime and the term 2 prime. Okay. And the term 1, in the term 1, they are both, so the term 2 are both what? Are both integration in the full domain. And they both involve what? They both involve, first of all, here is a Green's function. Here is a source function. Here, the Green's function, it actually integrates it integrates everything about the inhomogeneous term f. Here, this source function also concerns everything. We use the source function to integrate everything, okay, about this inhomogeneous term f xt. So that's a bit, okay? And the rest of it, okay, now for term number 1, okay, for term number 1. We're having that the term number 1, it concerns the initial condition, which is finite. Here, the term number 1, it concerns not the initial condition, but the boundary condition, which is H1. Right? So actually, what you can see is that these two things, these two formulas, they have very similar structure. They have a very similar structure, and the idea behind it is also the same. The idea behind it is that one is using the Green's function, and the other one is using the source function. And the source function or the Green's function can not only integrates the boundary value term or the initial condition term, but also integrates the inhomogeneous term. Also integrate the whole inhomogeneous term. Okay, and such structure, although I'm not asking you to memorize it, but such a structure, okay, is actually almost everywhere, okay, in the world of linear PDEs. Well, we have touched a little bit about that, okay. The idea of developing a source function or the Green's function based on setting up the delta function in the equation or in the initial conditions in a proper way, okay, and then using the same Green's function or the source function to solve the whole family of the questions. Okay, this idea is everywhere in linear PDE. Okay, and that's what I would. That's actually everything that I would like to say. Okay, for chapter 12. Again, I do apologize that I promised you that we would do a brief review, but we didn't do that. But what about we do that? We do something similar right now. So you have the book with you on hand. You have the book with you on hand. Okay. Let me tell you. Okay, one piece by one piece, which is going to be covered, which is not. Okay. Fine. So we'll be starting from chapter 4. Okay, we'll be starting from chapter 4. And you can stop me any time that you would like, and anywhere that you have a question. And I'm going to tell you, okay, which one is going to be covered, which one is not. So the separation of variables, problem 1, the separation of variables. The idea of using the separation of variables to solve the Dirichlet boundary conditions, the Newman boundary conditions, and for both wave equations and heat equations, they're going to be covered. You need to know how to do that, right? Okay. And there is a discussion in equation 12 on page 87. Okay, and that is about the base tone frequencies of a string. Okay, the frequency, the base tones of a string, and the fundamental notes
这欧洲
of a string and the
辅助
overtones
辅
of
助
a
你
string,
看
and how a string,
说哪来着？
if the note of a string is higher, will be higher or lower. Okay, and that such kind of discussion has shown up in chapter, I think in chapter 2 or chapter 1, I can't exactly remember, but that is something that's going to be covered. And the idea of eigenvalues and eigenfunctions for the second order differential operator x prime prime. Okay, that idea, okay, and that discussion, okay, the spirit of it is going to be covered. But I will not ask you what does it mean by a self-adjoint operator. Okay, this is not in the book, so that is not going to be covered. Now, okay, any other things about and why there is no eigenvalue that are positive? That discussion will also be covered.
So
Okay,
we
which is on-
should be more focused on the process of to deduce the formula, but not remembering the
True.
formula.
Yes. That's always, you can see that. You can see such kind of flavor in midterm, right? And the 4.2, everything, right? 4.2, because that's basically a repeating 4.1. And okay, 4.3 is not covered. What means condition? We can talk about anything about it. So that's everything about chapter 4. For chapter 5, okay, how do you compute the coefficients? Right? How do you compute the coefficients? That's going to be covered. And how do you apply the computation of coefficients to solve the wave equations and the wave equations and the diffusion equations? That's going to be covered. How do you apply Fourier sine series and the full Fourier series and the Fourier cosine series? Okay, and when is the good time? Okay, to apply those series. Okay, these things will be covered. And for example, if you apply a Fourier sine series, okay, yeah, let me put it this way. Yes, if you apply the Fourier sine series to fx equals to x, okay, then what would you imagine on the right hand side? What would you imagine on the side of pi?
On the what?
Use Fourier sine series. What would you imagine on this side?
It will suddenly drop to
Okay, it's going to drop real quick. Why that happens? Why that is happening? Because the Fourier sine series is going to be 0 on the both sides, okay, but not this function, right? So that's such a phenomenon. You should be aware of such a phenomenon, right? And if I'm asking you, so the next question is that true that the Fourier sine series is converging, okay, is converging pointwise in 0 and pi, excluding the both ends. They do converge pointwise, right? But do they converge uniformly? No, because there's always going to be a drop, right? Okay. So similar arguments for, and if I were you, I would pay a lot of attention to example 1, 2, and 1, 2, 3, 4, and 5 from page 108 to 110. Okay, these are perfect examples discussing what would happen if we're applying different types of Fourier series to the same function. Because by doing that, we're actually assuming, we're actually making different assumptions to these functions. And these different assumptions will actually bring us these type of jumps, okay, on both ends. So that's everything about 5.1. 5.2, what are the properties for the sine functions, for the even functions, all functions, and periodic functions, and how do you perform Fourier series for those? Okay, that's going to be covered. 5.3, orthogonality.
We won't cover the complex form.
Sorry?
We will not cover the complex form.
It will not, but okay. So in our class note, as long as I remember, in our class note, the complex form only took place at one place, which is on page 137, 5.5, when we are trying to sum up the Dirichlet kernel. Right. When we are trying to sum up the Dirichlet kernel, actually we need to use the help to express sine and theta, or sine and nx as in the complex form. Okay. It's only required over there,
So,
not nowhere else. Okay. So coming back to 5.3, orthogonality. Well, you should understand what does it mean by orthogonal of two functions. What does it mean? What does it mean by two functions are orthogonal to each other? What does it mean?
0 in the
Their
product.
inner product are 0. Okay, this is how they are defined, right? Okay, and the orthogonality is actually vital for us to define the idea of the Fourier coefficients, right? And symmetric boundary condition. What does it mean by symmetric boundary condition? To be able to make that call. Okay, make that judgment. And the idea that Dirichlet-Newman periodic Walling, they are all symmetric, right? And why there are no complex eigenvalues and negative eigenvalues for the second order differential operator equipped with symmetric boundary conditions. Okay, why that is true? Okay, you need to understand what the 0, 2, and 0, 3 in section 5.3. Okay. Section 5.4. Completeness, well, you need to understand, first of all, what does it mean by three different types of convergence. Pointwise convergence, uniform convergence, L2 convergence. Which one is the strongest?
Uniform.
Which one is the strongest in these three types of
Uniform.
convergence?
Uniform.
Uniform convergence, right? But is either uniform, is either pointwise convergence or L2 convergence, is either of the to be strictly stronger than the other? No, because we're actually having counterexamples in both ways, right? How do you make up that counterexample? Go back and check your class notes, right? And the theorem of the convergence, okay? The three different theorems of the convergence, theorem 2, theorem 3, and theorem 4. What you see is that these three types of convergence, they actually work for arbitrary Fourier series. Okay, that's why they are so they are having such a high demand, okay, in their requirements. For example, for the uniform convergence, it's actually requiring f(x), f prime x, and prime x to be existing and to be continuous. Actually, I'm talking about theorem 2 on page 128, right? But these conditions, okay, these conditions can be relaxed. Okay, these conditions can be relaxed if we are only talking about the periodic boundary condition, and or when we are talking about the other one, if we are talking about the full Fourier series. Okay,
不是我说
this can be
考
these
试
things
是
can be
是
loosened.
不能带期序的
And the L2 theory,
啊。
right? The L2 theory, we have defined what does it mean by the L2 norm and the L2 metric.
差不多有点
Okay,
好
for functions in L2 space. And L2 and the L2 theory is behind the idea of L2 convergence,
还
right?
考那个后面
And
就是
and the L2 theory also tells you that why if we are having, so you see, if we are having the norm, the L2 norm of each term of the Fourier series, okay, is constant, it's not declining, then we would absolutely have that for any L2
这
function,
个备注上
okay, for any function that is L2 finite, then its Fourier coefficients should be what? Should decline to 0. Actually, the sum of the square of the Fourier coefficients should decline to 0. That's actually pointed out by theorem 5 and theorem 6. Okay, and the least square approximation for the Fourier series. Okay, the idea behind that. Okay, so 5.5. The 5.5, the proof. Okay, the proof for the how do we perform the proof? Actually, this is going to be this is actually going to be I'm going to tell you it's going to be one question coming from the proof of the pointwise convergence, which is the first part of 5.5. there's going to be at least one question coming from that. Okay, 5 steps. Okay, 5 steps. First of all, the Dirichlet kernel, right? First of all, the Dirichlet kernel, and then proving that the Dirichlet kernel actually is related to what? It's actually related to a very specific type of Fourier series, which is the sine n plus 1 over 2 set.
这张你
And
重新看。
having that, this is also a Fourier series, and having that the function is L2. Okay, the function is L2. Then we will be able to prove the pointwise convergence. And such an idea is also extended to the discontinuous functions, which means that if the function is discontinuous, then what does its Fourier series converge to? Where does its Fourier series converge to? At the breaking points or at the discontinuous points? Half is actually the middle point of the left side and the right side, right? Okay, and the proof of the uniform convergence, that's actually a little bit more dedicated, so I won't require that. Okay, I won't require that for the proof of the uniform convergence. Gibbs phenomena, we didn't cover that at all. And well, the Fourier series solutions, there's actually the Fourier series solution actually is equivalent to our traditional methods of deriving these solutions. Okay, so this is the last part of 5.5. Okay, and then we didn't cover anything about 5.6, so forget about that. For harmonic functions, okay, for harmonic functions, yes, chapter 6. You need to know what does it mean by Laplace equation and the Poisson's equation. Okay, when I'm saying that, you should be able to know that. And the maximum principle, how do we prove the maximum principle? Right, how do we prove the maximum principle for a harmonic function? And how does the maximum principle is helping us to prove the uniqueness? Okay, that's actually something, the uniqueness of the Poisson's equation. And after that, the invariance of the Laplace in 2 dimensions and 3 dimensions, invariance under rigid motions. How to derive that? Okay, how to derive that? Well, I would require the derivation of invariance under rigid motions for 2D, but not 3D. Okay, 3D is a little bit more complicated. 2D, you should be able to comprehend that. And the next thing is that how do you obtain harmonic functions that are rotationally invariant? That's actually a big chunk of discussion on that, right? So we arrive at a log R or for 2D and 1 over R for 3D.
我可以把
Both
书
of
重
them
新看一遍。
have a singularity at the origin. Because then we have explained why there has to be a singularity at the origin. If there is no singularity, what will happen? It's going to be a constant because both minimum and maximum are. This is rotationally invariant, right? So on the circle surrounding the origin, it's a constant. So that has already. So if that is harmonic everywhere within the circle, that means that it's already attached its minima and maxima on the circle, which means that it can only be a constant. Therefore, if we want anything that's non-trivial, it has a singularity at the origin. Okay, and that function is actually, these functions are exactly the form of Green's functions. Okay, exactly the form of Green's functions. Later in chapter 7. Okay, now in 6.2, how yes.
Is this like R1 over R if you took Laplacian? Will it be the delta function?
Yes, not exactly the delta function. Actually, we talked about that. Actually, it's negative 1 over 4 pi multiply 1 over R. The Laplace of that is going to be the delta function.
Oh, how about the log R?
The log, okay, the log, same thing. Okay, same thing. Okay, you can. It's actually not so hard. You can do a differentiation by yourself and then check. The hint of that is how what parameter do you need to assign to the Green's function to make sure that you are going to obtain an integral to be 1 after the second order differentiation, right? Okay, 6.2, rectangles. Okay, rectangles. How do you solve so if, let's say if I'm having 4 different boundary conditions on 4 different boundaries, on these 4 different boundaries, how do you compute? Okay, how do you use the Fourier series to compute a solution? for the Laplace equation for that. And in the final exam, okay, if that becomes one question, I'm not asking you to solve I'm not asking you to solve the inhomogeneous, 4 different types of inhomogeneous boundary condition. It's going to be 1 inhomogeneous and 3 homogeneous.
Oh, great.
Okay, to save you from the computation. And yes, Q the same thing. Oh, by the way, a very quick stimulating question: what would happen if all of the 4 sides are homogeneous, satisfy homogeneous Dirichlet boundary conditions? What would happen if the 4 sides satisfy a homogeneous Dirichlet boundary condition? Homogeneous means what? 0.
Then maximum.
Then, which means that u equals to 0 on the 4 sides, and that will lead to
Constant.
0 everywhere. 0 everywhere. So the next one, Poisson's formula. The Poisson's formula, you need to know how to derive Poisson's formula, but I'm not asking you to memorize the Poisson's formula. Right? The Poisson's formula again is that how do you solve the Dirichlet boundary condition on a 2D for a circle? That's the Poisson's formula. Okay, that's the Poisson's formula. But again, how to derive that? You need to understand how to perform. So first of all, you need to understand how to change the coordinate from Cartesian coordinate to a polar coordinate. And second, you need to know how to perform the Fourier series, right? But if I'm asking you to do that, it's going to be step by step. It's going to be something like first you need to do what? Second, you need to do what? Third, you need to do what? Okay, I'm not asking you to derive the formula, which is equation 13 on page 168. Okay, I'm not asking you to do that. Mean value property. What does it mean by mean value property?
Every point is the average of the circle.
Okay, every point is actually can be regarded as exactly the average. Okay, as the circle surrounding for every point on the circle surrounding syntax is standard.
Professor?
Yes.
This is necessary to be a circle, right? We cannot put it to be a rectangle.
Actually, you are talking about the Dirichlet measure. You're talking about the Dirichlet measure for a non-circle boundary. Okay, which means that the Dirichlet measure means that what weight should I put for every point on the boundary if the boundary is not a perfect circle?
Oh.
And that's actually a very large open question for bizarre, especially for bizarre boundaries. Okay, in this case, so the best thing that we can say is that it's indeed still a weighted sum. It's indeed still a weighted sum for everything on the boundary, even if the boundary is not a perfect circle. But the weight is going to be very hard to compute. Okay, and that's everything about 6.3. We didn't cover anything about 6.4, so forget about that. Now, chapter 7. First grain size. Okay, first of all, divergence theorem. You need to know what does it mean by divergence theorem, which is the equation 1 in chapter 7.1. And the first Green's identity, which is this equation G1, okay? And second Green's identity, which is the first equation on 7.2. And how do you use the first Green's identity to derive the mean value property? Okay, not for a circle, but for an empty sphere. Okay? And how do you derive the uniqueness? Okay, again, not using the maximum principle, but using the energy method. Okay, and now for the Green's identity. So for the second Green's identity, we use the second Green's identity to derive a representation formula for the harmonic function, which is equation number 1 for 7.2. Again, I will not ask you to memorize that, but you should know how to derive that. I may ask you to derive it. Okay, for example, giving you the second Green's identity, and I'm asking you to derive that. Okay, and this is actually a perfect chance for us to connect to chapter 12. Yes. Okay. 7.3, we didn't spend a lot of time on the Green's function, so I'm not asking you about the specific requirements for the Green's function, but we need to know what's the spirit of the Green's function.
Professor, I have quick 2 questions regarding to Green's function.
Yes.
First, is green function only defined with respect to Laplace equation?
The similar ideas. Okay, so in this case, let's say Green's function is only defined for the Laplace equation, but the Green's function, the idea of the Green's function is actually generalized for arbitrary type of linear ODE or PDE. For ODE, we also call that G to be Green's function.
Okay. And the second question is, a G is to be an V plus H, where H is a harmonic function and V is something like, we only talk about the specific V, which we choose it to be negative 1/4 pi.
I'm asking you, I'm only asking you to know that, nothing else.
Okay, so actually we can choose this V to be more arbitrary.
You mean the selection of G? Selection of Green's function?
Selection of V.
What do you mean selection of V?
V plus H, where H is a harmonic function and V has a property that is.
Can you please tell me which page are you talking about?
Okay, 188.
188, okay, and which line?
The last four line. Now let's write Gx equals.
Oh, okay, I see. Well, no, the V cannot be chosen arbitrarily.
Okay.
Yeah, it cannot be chosen arbitrarily.
It needs to be
这节
chosen
课
as
是
this
不是
specific.
Yes,
6
that's
号是不是
right.
讲了说拉那个马格老日？
That's why it's so important.
还是准备。
Okay, 7.4, we can cover anything about that. And then chapter 12, well, there's no, we didn't successfully set, I mean, talking about things in a very rigorous fashion, but at least, okay, you should understand what does it mean by what I'm saying, distribution. What does it mean by the convergence of distribution? What does it mean? Okay, for example, when I'm saying that the Dirichlet kernel is converging to delta x, what does that mean, right? And the source function, when t equals to 0, that's converging to a delta function. What does that mean? These two delta functions are two different delta functions. Why they are different delta functions, right? Okay, that's it. That's everything. Okay, and you know what? I have a change of plan for the last homework. I'm going to release the homework. Okay, but I'm not asking you to submit it. Okay, so feel free to do it or not. And the answer key is going to be released this week. Okay. Any other questions? No? Yeah. Oh, sorry. Still, I have one more requirement. Can you please do the teaching evaluation? Yeah, before you leave.
Oh my.
Yeah. I do apologize for that, but there's only 4 people who have submitted their teaching evaluation, and my goal is 16. Everyone. Okay. So if you can do that right now, I will be really appreciative. I understand this has been a very long day.
我把录像停了。
Yeah.
我刚才非常不好，一点都没有听，我就纯靠录像了。